It's 11:47 p.m. An AI coding agent just finished reading a 200-page codebase. It generates a diff, refactors a gateway adapter, and commits the code. The tests glow green. But the developer double-checks the commit and realizes the agent edited the completely wrong file. The real gateway adapter was 2 directories over. The agent had the correct path sitting right there in its memory, but it confidently wrote a test against its own mistake. This happens constantly in production. These agents don't fail because the model lacks intelligence. They fail because dropping 1 million tokens into an unmanaged context window inherently creates chaos. The industry narrative says we just need bigger context windows. 200,000 tokens, 1 million tokens. The promise is simple. If it sees more data, it makes better decisions. Expanding a model's context window on the x-axis causes baseline accuracy on the y-axis to drop steeply, the lost in the middle effect. But our treatment line, using the disciplined Pratyakṣa memory harness, maintains a flat, stable trajectory at maximum accuracy, regardless of window width. Pouring more unmanaged text into an AI's memory doesn't clarify its thinking. It actively degrades the system's ability to retrieve valid information. We keep trying to fix this by patching prompts, which is like pouring a chaotic funnel of mixed text blocks straight into a brain. The actual fix requires structured shelving. This is context engineering. It is the explicit, auditable management of exactly what an agent knows, why it knows it, and precisely when a piece of evidence needs to be retired. To build that structured memory, engineers realized they needed a precise vocabulary of logical operators to stamp data before it enters the AI's window. Strangely enough, those exact mathematical operators were formalized by logicians in 14th century India. This classical Indian epistemology, specifically from schools like Nyāya and Advaita Vedānta, spent centuries mapping out how to handle streaming evidence. They built a relational logic of operators that perfectly models the mechanisms missing from modern computer science. Fixing the memory architecture of a modern AI turned out to require a millennia-old logical framework designed to define what counts as a justified belief. Traditional models run into trouble because they treat the act of gathering information and the act of making a decision as a single cognitive step. If an agent scans a messy file and immediately tries to answer, it hallucinates. This system structurally divides the work. First, the Monas node rapidly scans documents to surface evidence without attempting to answer. Then, the Booty node evaluates this evidence, filters out invalid data, and isolates the single final answer. By strictly separating the attention phase from the judgment phase, the agent loses the ability to confidently invent facts that aren't there. But the system still has to decide which facts to trust. It does this through a protocol called Avachadaka. Every single piece of retrieved data is tagged with its strict limiting conditions, like its timestamp or source precision, before it ever enters memory. When a 2025 document conflicts with a 2019 claim, the system triggers BADA, or sublation. Instead of deleting the old data, the 2019 block dims and slides into a permanent audit track, while the 2025 block takes precedence. Sublating data instead of deleting it preserves a perfect operational provenance. An engineer can read the audit log later, and the AI only acts on the most current truth. During long operational tasks, artificial agents also suffer from severe system prompt drift. Over time, they simply forget their initial instructions. To prevent this, the harness maintains Sāṃkhya, a locked, immutable witness state containing the working directory, model identity, and core policies. Because this invariant state survives every memory compaction event, the agent maintains its foundational rules and guardrails, whether the conversation is 3 turns long or 300. To see if this actually works in practice, researchers ran a head-to-head A/B test on Swebench, pitting baseline models against the Pratyakṣa harnessed agent on complex software engineering tasks. This bar chart tracks target path hit rates. Under strict limits, the unaided baseline agent anchored on wrong file paths, degrading to a 50.3% success rate, a random coin flip. Under those exact constraints, the harnessed agent's treatment bar climbs straight to 100%, hitting the target in all 120 paired runs. Context engineering takes the chaotic guessing out of the process, producing deterministic, perfect recall. The data matrix for this research is deliberately transparent, showing null results like the truthful QA test right alongside the major successes. The study also specifies its constraints. The head-to-head tests used a deterministic patch simulator rather than live code generation, and the sweeps were limited strictly to anthropic models. Acknowledging exactly where the system's boundaries lie doesn't weaken the findings. It proves the rigor of the testing and confirms that the directional data is scientifically valid. The most practical part of this framework is its weight. There is no heavy machine learning stack to download and no core architectural models to fine-tune. The entire harness is a 46 kilobyte plugin that installs directly into standard developer environments like Claude Code or Cursor in about 30 seconds. Context engineering provides the operational discipline that large language models have been missing, and the tools to implement it are ready to deploy today.